at this point, we just solved the two subproblems. The first subproblem, when we apply the brute force method. Our first method is the brute force method. In that method, when we apply additions, we only count the number of additions. We get n additions and the corresponding number of units, n units. N units of time that we used. Before you leave, just remind me attendance check. Okay, you too. Yeah. All right. Our second subproblem, this is the number of multiplications. But we need to convert it to the time units so that we can calculate the total number of time units. So we multiply 10. After we multiply 10, we get this number. This many units. Then we add up because we need to calculate the total number of units. So this is the total number of units. All right. After this step, the next step, we want to do improvement. Because remember, in a previous slide, we know we can do something different, right? Yeah. X to the fourth, we can use 2 multiplications instead of 3. So that simple example tells us we can do better than this one. We can do better than this one. Yeah. So we know it's possible. If it's possible, then that means our next step, we work on the improvement. We want to do the best we can, right? When we do improvement, we want to do the best we can. Yeah. All right, so here, before we start, there is one important question I want to ask you. The strategy, problem-solving strategy. So here I emphasize the importance of problem-solving strategy. All right. Here, when you do the improvement, you have two places to work, right? 2 parts to work. The first part, addition part. The second part, multiplication part, right? Yeah. So the first part, you try your best to reduce the number of additions. The second direction to go, you try to reduce the number of multiplications. Okay? Yeah. So here the question is, which direction we want to go? We need to make that decision first. Which direction is better? We need to make that decision. Yeah. All right. So here, I want to look at this question from a general problem solving. General problem solving. Okay. All right. In that general problem solving, we need to use our resource to solve the problem, right? Yeah. So when you solve a hard problem, you need to use a lot of resource. Yeah. And usually, our resource is not unlimited, right? Our resource is not unlimited. Yeah. Usually, resource always limited. Yeah. So when you have precious resource, but there are several parts of the problem you can apply your resource. When you need to make that decision, which part you want to apply your precious resource? That's a general problem solving question. Which part you want to apply your precious resource? The resource is limited. If you apply here, then you cannot apply another part. Yeah. Yeah. You only need to select one of the parts to apply your resource. Well, you need to make that decision. What is the best decision to make? That question, that general question. Yeah. Based on your intuition, so here, yeah. So you have the real world experience. Based on your real world experience in that situation, what is your natural decision to make?
Between the addition and multiplication.
Yeah, yeah.
Well, the multiplication, I mean, it's a 10x performance cost, so it seems like that would be the way to start.
Yeah, yeah. He said we should put our resource on the reducing number of multiplications. Do you feel it's a good decision? Yeah, yeah. All right. Yeah. If you say the good decision here, based on your intuition, can you explain why it is a better decision than you apply your resource on addition part? Addition part. 10 times more important, right? That's the 1-to-1 ratio, right? 1-to-1 ratio, 10 times important. Do you also compare the numbers? Because when you say 10-to-1 ratio, you do not compare the numbers, right? There is a number factor there, right? If you factor in the numbers, what is that ratio? What is that ratio? So here, multiplication part, this many units, right? Addition part, this many units. What's that ratio? Okay, if you do the ratio, is it 5m plus 1 to 1 ratio? Is that the ratio? Regarding the number of time units, is that this ratio? Yeah. Yeah. Because this is the units multiplication. So the numerator, this many units. Denominator, this many. You cancel out one n. Okay, you cancel. So this is the new ratio. Is that big? Yeah. Here we imagine n is very large. N is very large. Okay. So that's big, right? Yeah, that's very big. Yeah. All right. That's very big based on your intuition. Yeah. All right. So here, let me draw this big circle representing total number of units we use to solve this problem. Then we divide it into two parts. Yeah. Addition part, this small. Okay, this is addition part. This small. This is a multiplication part. So that big. Okay, all right. If we put our investment in the multiplication part, then we have more room to improve, right? That large part. So how we have more room. This is the room to improve, right? We have big room to improve. For addition part, the best you can do, reduce the addition part to none, right? But you still have the big part left, right? Yeah. So here, yeah.
Reduced it by just taking away all of the instead of 6n, n plus n plus n.
Yeah.
We still have 6 multiplication, which is less than the 10 multiplication.
Yes. So that observation tells us if you put your precious resource on the smaller portion to improve, you waste your resource. So you should put your precious resource on larger portion. So this observation is summarized as a law. So people call it Amdahl's law. Amdahl's law. Yeah. Amdahl's law tells us so that we can treat it as a general problem solving strategy. Amdahl's law tells us, use one short sentence to describe Amdahl's law. Focus on common case. Focus on common case. Focus, okay? Yeah. Put a resource. Most common case, right? The multiplication here we treat as the common case, right? Yeah. Because the fraction part of the time unit used on multiplication is larger. What's the common case? Yeah. The execution time used for that part is the largest. Yeah. So that's the, yeah. Here we call it Amdahl's law. Yeah. So that tells us our next step. We should try our best to improve multiplication. Yeah. All right, so let's do it. Yeah. All right. How to reduce? Yeah. Improvement strategy. Yeah. Here I already explained 2 parts. Yeah. So here we can do a little faster. Yeah. Yeah. Which part? Yeah. Observe it. Yeah. Yeah. 10-to-1 ratio, but also there is a number factor, right? Yeah. All right. Focus on the major part. Yeah. So the conclusion: focus more on the multiplications. Yeah. All right. So the new question: how to reduce the multiplications? Yeah. Yeah. All right. B.3 Horner's rule. That's the important algorithm. Yeah. Horner's rule. Yeah. So let's learn this new algorithm. Yeah. All right. Our goal: reduce the number of multiplications. Yeah. Our strategy. Because in our problem solving, yeah, we always need to apply certain strategies. Yeah. Every step, when we feel it's hard to solve, we need to think about some strategy, effective strategy. Here, it's hard, right? How to reduce the number of multiplication? It's hard. So now we need to think about some strategy. The strategy study simpler case. Because if you solve this general case directly, here, this n, degree n polynomial, how to reduce the number of multiplications, then it's too hard. We don't know how to reduce. All right. So in this situation, the strategy, study simpler case. Can we try relatively smaller number n? When n is large, it's hard, right? If I ask you, I give you n 100, it's hard. Is it better we try some relatively small n? Yeah. So then we feel we can handle it, right? If I give you 100, then most of you feel we cannot handle it. Yeah. Too complicated. All right. Then we have freedom to change that n, right? Yeah. We have freedom to change that n. Yeah. So which n do you want to select? We have freedom. Yeah. So you need to make some decision. You need to choose appropriate n to work on it. Yeah. So which one you want to choose? Simpler, much smaller than 100. No. Yeah, 2. Yeah. So it's not a 0, not a 1, it's 2. Why is that? Yeah. First, we want to get a small n number, right? But 0 smaller, 1 smaller, but does not help. N equals 0, it does not help. Okay? We do not get any useful information. If it's 1, it does not help. Right? Yeah. It's small, it's simple, but it doesn't help. Yeah. So the first meaningful example is n equals 2. Because we want to reduce amount of work, but we need to do some work, right? Yeah. Yeah. If you choose 0 or 1, there is no work to do. No work to do. So there is no gain. Yeah. So here we need to do small amount of work. That's why we choose n equals 2. All right. Yeah. So let's get our hands on an example with n equals 2. Yeah. All right. Yeah. Then when we work on n equals 2, yeah. Yeah. So let's write the polynomial explicitly. There are 3 terms. 3 terms. Yeah. Then you do observation on this expression. Yeah. We need to discover some property. We need to discover some critical property. When you make your observation on these 3 terms, can you see something special, some property? Special property? Try to compare these terms. Anything special? No. Because that property, we will use it to help us do the job. So that's important. So this step is important. Right? Yeah. Yeah. So this step is critical. Right? Yeah. So if you look at these 2 terms, can you see some property? Last 2 terms. Can you see some property, special property? Yeah. They have common factor x. They have common factor x. That's the property. Okay? That is the critical property, common factor x. When they have a common factor, yeah, the first thing you want to do, factorization. Factor it out. Factor that common factor out. Okay? Yeah. So we do a factorization step. The next step is factorization. Yeah. So you write the last 2 terms in this new way. Yeah. After this step we call the transformation. We change the form, but without changing its value. Yeah. These 2 expressions are the same, right? Left-hand side expression, right-hand side, they are the same, but they have different structures, right? Yeah. They have different structures. Yeah. Correct. Yeah, correct. So the different structures will give us different number of multiplications. Yeah. So we want to see different structure, yeah, because the result it will give us different number of multiplications. So let's count the number of multiplications. The first one, 3, right? 1 plus 2. The first term you need 1 multiplication. Second term you need 2 multiplication. So total 1 plus 2, 3. Tell me how many for the second? 2. Yeah. Yeah. Right. So he said it's 2 multiplication. Let's count. The first one, x times this parenthesis, that's 1, right? X times the whole parenthesis, that's 1. The second one, a2 times x, that's 1. 2. Addition, we do not count. Addition, we do not count. So there you can see it's an improvement. The reduction from 3 to 2. 3 to 2. How about that progress? Yeah. When n equals 2, you make it this many reduction. This many reduction. Okay. It's encouraging, right? Yeah. Yeah. At least it's encouraging, yeah, because yeah, we feel this is the right direction to go. Yeah. Do you feel we should go along the similar direction to solve the whole problem? Yeah. All right. So our conclusion is factorization is the main technique that helps us to solve this problem. Main technique, factorization. Yeah. All right. So for this special example, our gain is from 3 to 2, reduction 1 by 1. All right. Summary. Yeah. Here you can see through the factorization, we change the order of evaluation, right? Yeah. Because the way we apply multiplication, the order is different. In these two structures, the order of the operations is different. So that means we can change the order by factorization. So let us keep doing factorization. So here we can also say factorization is the key to the success, right? Yeah, key to the success. Yeah. So if you understand this point, the factorization is the key to the success. What you should do next? What you should do next? Yeah, factorization. Yeah, helps us make significant improvement. So, what is your decision next? Yeah. Because we need to consider the general case. In the general case, what is your decision? Based on our experience, we have some experience. What is our decision in the next step? Yeah. All right, let's keep working. Yeah. Keep working. Yeah. If you do not have that strong sense on our next step, yeah, that means we need to collect more experience. We need to, yeah, because you do not have strong feel at this point. Yeah. So in order to strengthen your understanding, yeah, we need to do another example. Yeah. This example is n equals 3. Okay? Yeah. So let's work on another one. Yeah. To get a stronger understanding. All right. So let's consider how to apply factorization to reduce the number of multiplications for n equals 3 case. Yeah. Yeah. Still factorization, right? Yeah. Still factorization. But this time your factorization, what's the coverage of your factorization? How many terms can you work by factorization? 3, last 3. Yeah. Last 3 terms. Yeah. Yeah. Not last 2 terms, right? Last term not as good as covering last 3, right? Yeah. Yes. Here you can see when we apply the factorization, we want to cover as many terms as possible, right? Yeah. So that is another strategy. We want to apply our key to the success method. Factorization is the key to the success method. When we apply that effective method, we want to cover as many terms as possible. Yeah. So we get a factorization here. Do you feel good enough here at this point? So we factorize x out, covering last 3 terms. Do you feel good enough? Why not good enough?
We can still optimize inside the parentheses.
Yeah, good. Because we can do more improvement inside the parentheses. Yeah, good observation, good sense. That's good sense. Yeah. So let's do another round factorization. How about that? So here you can see, because factorization is the key to success, that means whenever we have a chance, we should apply factorization, right? Whenever you see some chance, you should apply factorization as much as you can, right? As much as you can. Now we can apply another round. Yeah. So the second round factorization, yeah. So we get this result. Is it good enough? Think about it. Because now, in this new representation, we have no chance to apply another round of factorization, right? Yeah. That's the end. That's the end for factorization method. Yeah. All right, do the counting. Do the counting. Before we apply factorization for the original formula, how many multiplications do you need for the original formula? 1, 2, 3, 1 plus 2 plus 3. So you need 6 multiplications. Okay, yeah. 6 multiplications. All right, yeah. Here, okay. So 6 multiplications. Yeah. All right. Now, how many for our newest expression after 2 rounds of factorization? How many? 1, 2, 3. So you reduce the multiplication number from 6 to 3. Is it bigger? Yeah. Correct. Correct. Yeah. Yeah. He moved another step further. When a equals 4, we reduce from 10 to 4. Okay? Yeah. Here you can see the improvement becomes larger and larger, right? The larger the n, the bigger the improvement. Good observation. Yeah. All right, so here I want to do summary a little bit. Yeah. All right, because next step we need to move to the general case. Before we move to the general case, let me do a summary here. Okay, all right. Why we can do this big improvement? We can treat it as big improvement because we apply the effective factorization method to the extreme, right? As much as we can, to the extreme. Okay? Yeah. So that approach, there is a special name for it. We call the greedy algorithm. Greedy algorithm. Yeah, so what's that? Because we apply certain method as much as possible in a greedy way. Okay? We apply certain method in a greedy way. So what's that greedy way? Okay? We apply it to the extreme. Okay? So we call it the greedy algorithm. Here I introduce this greedy algorithm. Yeah. All right. Yeah. So I will talk about this one. Later, we have several places we need to apply this greedy algorithm. For the greedy algorithm, you need to have a greedy strategy. So each step, you need to have a greedy strategy. How to make it greedy? Okay? How to make it, for example, how to make it greedy? In the first round factorization, you make your factorization cover as many terms as possible. That's our greedy strategy. Okay? Because we make our first round factorization covering as many terms as possible. That's our greedy strategy. Okay? Yeah. Second round, inside parentheses, we also apply the greedy strategy. So we make our second round factorization covering as many terms as possible. That's our greedy strategy second time. Yeah. Okay? Every round, you need to apply your greedy strategy to the extreme. And you want to get the best result. Yeah, so here. All right, our last step. Yeah. Last step, this time for the general n. All right, all right. Let's do generalization. This time, we do factorization as much as we can. Round by round, okay? Every round covering the maximum number of terms by the factorization, okay? Yeah, the greedy idea. Yeah. All right, so this is a greedy algorithm. Yeah. Apply some property as much as we can at each step. Yeah. All right. Here, at each step, it tells us we do our best locally, right? Because each step, it's a local consideration. It's not global consideration, right? Yeah. Because you only consider one step. Yeah. So it's a local consideration. So not global. Yeah. So here you can see the greedy algorithm lets you do the best you can locally, but not globally. Okay? Yeah. Globally, you may not get the best solution. Even each local step, you do the best you can, but globally, you may not get the best solution. Yeah. So that's the greedy limitation of the greedy algorithm. Greedy algorithm does not guarantee you get the best solution globally. Okay? Yeah. Because when we say the best solution, it must be a global best solution. Okay? Yeah. Yeah. So sometimes if you are lucky, you can get the best solution. But sometimes if you're not lucky, you won't get the best solution. That's the limitation of the greedy algorithm. Okay? So you need to double check. You need to double check if your greedy algorithm results in the best solution or not. All right. So that's the basic property of the greedy algorithm. Okay. So here the conclusion is the greedy algorithm is locally optimal. Yeah. Yeah. Easy to achieve. Yeah. It may not be globally optimal. It may not be overall optimal. Okay. Because it could be very hard to get an optimal solution. Yeah. So in our algorithm, to get an optimal solution, very hard. Yeah. Yeah. Very hard. Yeah. All right. So the greedy algorithm is a relatively easy way to solve the problem. Yeah. Yeah. But you need to be very careful. You may not get the best solution. Yeah. All right. Yeah. Now let's do our last step. Factorization. Yeah. Yeah. Now the first round easy, right? Yeah. We have a lot of experience. Yeah. So now the first rounds, yeah, based on this example, first round, second round, okay? Then keep doing round by round. At the end, we can write factorization in this final formula, right? That final formula. Yeah. At the end. Okay. Now you count number of multiplications. Can you tell me, in that final formula, how many multiplications do you need? Final formula. Yeah. As a practice exercise, can you tell me how to find the number of multiplications? Remember, I introduced one basic counting method before. When you have that situation, counting situation, last time I talked about one counting technique. It's called counting by reference. Here, can you apply counting by reference to find the number of multiplication? Can you find appropriate reference object? Reference object? The first multiplication occurs here in this parenthesis. Can you associate with one object that is easy to be identified? Some object, you can associate with that subscript. 1, right? The second multiplication occurs here. Can you associate with the second subscript? And so on. Keep doing. Do you get a 1-to-1 correspondence? The last one, right? Last one associated with this last subscript. Do you get a 1-to-1 correspondence between multiplication object and the subscripts object? For multiplication object, hard to keep track of, right? Hard to keep track of. But is it easier to keep track of the number of subscripts? you associated with how many subscripts do you have? I mean, use the n number. How many subscripts? Starting from 1 consecutive integer through n, how many subscripts? N, right. Number of subscripts n, then you go back to the number multiplication also n. That's counting by reference. Okay? So when you see the similar situation, first try to identify the situation. We want to do the counting. But the original objects to be counted, hard to keep track of. Hard to keep track of, yeah. Because their identification is not quite clear, right? There is no clear ID, for those objects. Yeah. So now we do the mapping. So we map to a different set of objects, but the new set of objects, they have clear identifications. Yeah. So we do the counting on the easier objects. Yeah. So then we get the answer. Yeah. All right. This gives us the Horner's rule. Yeah. Yeah. Horner's rule. Horner's rule tells us when you evaluate polynomial, you do this factorization and you use this way, so you only need n multiplications. Yeah. N multiplications. Horner's rule. Okay? Yeah. Yeah. All right. Yeah. So after this, then we want to do in comparison. How much is the improvement? After we derive the better algorithm. If we go back to compare with the brute force method, do you have some idea how much better improvement we get by Horner's rule? Yeah, it's better, but can you have a, clear understanding how much better? We know it's better. Yeah. Yeah. We know it's better, but can you describe how much better, right? How much better? Okay. Yeah. So if I ask you this, all right. If before the improvement we need to use certain amount of time, if after improvement we only need to use 1% of all the time, do you think it's much better? Only 1%. 100 to 1 improvement. Do you think it's a very good improvement? You only need 100th of the time, original time. Yeah. Do you think this improvement can achieve that? 100th of the original time. You don't believe? Yeah. I see you nodding. Shake your hand. So you do not believe it, right? Yeah. Anyone believe it? So using the Horner's rule, we can improve efficiency with 100th of the time. Believe it or not? Believe it or not? Yeah. He does not believe. Do you believe?
Depends on how big n is.
Yeah, how big n is. Oh yeah, here. Yeah, that's correct. Yeah. Here I tell you how big n is. Yeah. I'll tell you how big n. Because for a question like this, our main focus is on very large n. Okay? We don't worry about small n, right? Because our computer is so powerful, nobody worry about this relatively small n, right? But people worry about the huge number of n. For example, n equals 1 million. Then we may get trouble, right? Yeah. For n is relatively smaller, 100, 200, even 1,000, people don't worry. We don't worry about n equals 1,000. Our computing resource so powerful, so we don't worry about that. But we worry about 1 million, 1 billion, 1 trillion. We worry about that. That huge n number. Question.
Is there like a formula to know how much?
Yeah, yes,
Would it be?
yes, there is formula, there is formula.
2 to the n minus 1?
Right, yeah, all right, let's look at that, okay? Yeah, so here I raise the question, yeah, but back to you, you do not believe 100th of the time, yeah.
You're saying, like, are you asking, will that be like 100 times faster? Is that what you're asking?
Yes, yeah.
I think it could,
So you believe it? It's possible, right?
at super high.
Yeah, super high. Yeah, super high. Yeah. You imagine it could be super high. Okay? Could be super high. Now you believe it, right? Yeah. So yeah. All right. So let's look at that. Yeah. So here, give you the idea in algorithm. So here, at this point, yeah, because in our algorithm, when we study the efficiency of the algorithm, our focus is on very large n. Here, this n we call it data size. So our main focus is on very large data size. Okay? For relatively small data size, we don't worry. Okay? So nobody worries about for relatively small data sizes. Yeah. So if we can handle very large size, then we don't worry. Yeah. Okay. All right. The last step, last topic, visualize performance improvement. Now, because it's hard to imagine, so we want to visualize a little bit. So we draw the picture to show you, so you get a better feel about the huge difference. How large is the difference? Yeah. That 100 to 1, not big enough. That improvement is not big enough. Yeah. So the actual improvement much bigger than that. The actual improvement much bigger than that. Okay. All right. So let's work on some concrete examples to see the huge difference. All right. Yeah. Because our improvement occurs in this part, right? So number multiplication from this many after reduction to this many. Okay? That's the key point, right? Yeah. The reduction place. Yeah. Reduction place. All right. Yeah. So we want to see the impact of multiplication reduction. Yeah. All right. So we want to try something so we can feel about it. Yeah. So these two formulas, it's hard to feel about it, right? Yeah. These two formulas too abstract, so you cannot. Although the difference is big, but you cannot feel about it. Yeah. So here, we want to work on some concrete examples to feel about it. Yeah. All right. The first example, let's try n equals 1,000. Oh. Okay. My pen does not work. Yeah. Oh, it works. Yeah. That's scary. Yeah. Yeah. The first example, n equals 1,000. We do not treat 1,000 as a big number, right? Yeah. So let's work on this number not that big. Okay. Yeah. So 1,000, the difference is 1,000 to 500,000. 500,000. That ratio. Yeah. If you look at the reduction, so that ratio, take ratio. 500 to 1 ratio. Yeah. Bigger than 1%, right? Think about it. When n is 1,000 already, our improvement is better than that 1%. Because 1 over 100, or 1 over 500, 1 over 500, that improvement already beats that example. Yeah. All right. Next, let's try 1 million. N equals 1 million. This time much larger. All right. Then let's plug in. Yeah. And 1 million. Left hand side, we plug in. Yeah. How large is this number? Can you call it? Yeah. 500 billion, right? If you take the ratio, what's the ratio? Yeah, right. Yeah, 500,000. 500,000 to 1 ratio. 500,000 to 1 ratio. That big. That big. Okay? All right. Then, even if this ratio is so huge, still hard to feel about it, right? Yeah, because you see that big number, but still not quite straightforward for you to feel about it. So here I want to give you another way to feel about it. So you really feel about it. Yeah. So here, that is, let's assume, so this is the old method, sorry, old method is here, right? Old method is here. The new method is here. Yeah. Yeah. So we solve the same problem if we use the new method, yeah, because that one I use 1 second. How about that? 500 million to 1, so that one I use 1 second. Then, if you use the old method, if you use new method, 1 second, you can get a result. If you use the old method, you need a 500,000 seconds. Okay? Yeah. If you use the old, you solve the same problem. Old method, you need that many seconds. Now let's convert to number of days, right? Yeah, because we don't know how long is that time, right? If you convert number of days, 5.8 days. 5.8 days. Yeah. Okay, yeah, 5.8 days. Yeah. But solving the same problem, huge difference. Solving the same problem. Yeah. Here you can imagine, yeah. Suppose some real world problem, we need to evaluate 1 million polynomial. Okay, so that huge polynomial in real world application problem. Okay, all right. So if you do not apply the best algorithm, here we treat this as the best algorithm, the cornerstone, best algorithm. Okay, so if you do not apply the best algorithm, you use the brute force algorithm. You need to wait after you hit the enter. You need to wait 5.8 days to get the answer. That long. Okay? Yeah. So that's the older method. Yeah. All right. You can imagine. Yeah. But if you use the new method, you hit the enter, after 1 second, you get the same answer. How big is the improvement? How big is the impact of efficient algorithm? Here the reason is because we use that efficient algorithm instead of non-efficient algorithm. That's the huge impact. Okay? Yeah. Yeah. So here is using this example, I try to convey. So in the real world applications, you want to develop the best algorithm you can get. Okay? Yeah. Because the gain is huge, right? Think about it, the gain is huge in the real world. Yeah. Okay? Yeah. All right. Yeah. All right, so we finish part B. Yeah. So at this point, so we finish part B. All right. So we still have some time. I want to go to part C to get it started. Yeah, so part C, The topic, role of data structures in algorithms. Yeah. Although our class focus on algorithms, but we need to talk about data structures a little bit. Yeah. 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 Our last module is about data structure. Yeah. Last module is about advanced data structures. Yeah. All right. Yeah. But here, let's look at the, we want to understand how the data structure can help improve the algorithm. Yeah. Here. All right. C.1, search unordered arrays. Yeah. Our problem number 2 in this class. Search an unordered array. Given an unordered array and a search key. Search. We want to find which element has the value that matches the search key. Okay? Find index I such that k equals a of I. It's a simple question. Yeah. Simple question. So we just do comparison one by one, right? Yeah. From beginning to end. That's all we need to do. Yeah. 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 So here, for this class, we will work on 3 basic types of the problems. Yeah. The problem type. So this one is the search type. Yeah. So for this class, we will do search, sort, and selection. That's the 3 basic types of the question. Yeah. Search, sort, and selection. Yeah. So this one is our first search problem. Yeah. Yeah. The data structure, we use array. Simple, very simple array. Yeah. All right. Yeah. So, here, so reference section 2.1. All right. Yeah, so here, first we understand why data structure is important in problem solving. So this question is related to the question in our first class, that chessboard. In the chessboard, there is an important step, organize the data. The original given data are very messy, right? Yeah. You need to find a way to organize your data. Yeah. Yeah. So this tells you why we use appropriate data structures, because we want to organize our data. We choose appropriate data structures because we want to organize our data in a friendly way. If we organize the data in an efficient, friendly way, they can find our data quickly. We can locate the data faster, more efficient. All right. Through data structure, we can make our data well organized. Then the search cost will be smaller, right? Because when you search data, there is a cost, search cost. But if you organize the data in a nice way, then you can find your data much faster. So that's the reason we choose good data structure. All right, find the required data faster. And the result, we want to have the better performance. All right. Here, let's do analysis. Let's look at this example. This example, unordered. So here, unordered. So we do not order the data, because to order the data, there is a cost, right? If you want to make unordered data ordered, you need to do the sort. You need to sort it. When you sort it, there is a high computation cost. So we will do sorting next. Our next step, we will do sorting. But the cost is high. When you do sorting, the cost is very high. Okay? Yeah. So here, we don't want to spend our resource on sorting. Okay? So our resource. Sometimes we want to spend our resource on sorting. Sometimes we don't want to spend our resource on sorting, right? Yeah. Because we feel not worth it. Sometimes we feel sorting, not worth it. Sometimes we feel it's worth it. So we will do it. Yeah. Here, we don't want to sort it. So let's find the given key without sorting. Yeah. Without unordered array. All right. We do comparison one by one, sequentially, from beginning to end. So each comparison, we compare k and the current element. And we start from the first element, I equals 0, first element. For the comparison, there are only two cases. K equals the current element, or k not equal to the current element. Yeah. If not equal, if equals, then returns I, that termination. Our program terminates. Otherwise, we need to do more iterations. Compare with the next element in the array, and so on. Okay, yeah. But at the end, when we reach the last element, yeah, when we reach the last element, if we cannot find the given key in the array, we need to send some special information to the user telling them the key is not found, right? Yeah. So here, yeah, this special -1, yeah, special -1 number tells, because it's not a valid index, right? Index, because if you can find some element matches the given key, you will return a valid index number, 0 through n-1. But -1 is not a valid index. So it tells us the key cannot be found in the given array. Then you are done. Yeah. So that's the, the whole algorithm. Very simple. Yeah. Everybody understand that. Yeah. All right. So after that, now we want to do some analysis. Yeah, for this simple question, but we want to extract some useful information here. Yeah. All right. Yeah, let me ask you a few questions. Yeah. Yeah. Here. Yeah. So we call it sequential search or linear search. Yeah. So this algorithm, sequential search or linear search. Yeah. All right. Then let's do some discussion. We want to see how fast it is. How fast it is. We want to describe its performance or its efficiency. How fast it is. Yeah. Yeah. How do we describe its efficiency? Yeah. Yeah. Some function. Yeah. Some way. Some function. Oh yeah. Here. Remember last time I mentioned some efficiency measure, right? Remember in our discussion before, I talked about efficiency measure. Yeah. Here, can you tell me what efficiency measure should we use here? Efficiency measure. How do we measure efficiency? Right, number of comparisons. Because this measure does not rely on hardware, right? This measure does not rely on software, hardware factors. Yeah. So it's a objective and stable measure. Yeah. So let's look at the number of comparisons here. All right. Count the number of comparisons. Yeah. Yeah. But here there are many different cases. Yeah. Because the given key K, if this given key K equals different values in the array, then the number of comparisons will be different, right? Yeah. If the given key equals the first element, you need one comparison. If it equals second element, you need two comparisons, and so on. Right? Yeah. Yeah. So the last element equals the last element, you need n comparisons. Yeah. And there is another case, no match case, you also need n comparisons. Yeah. So here, the next question is, if I ask you to describe the overall performance of this algorithm, which number you feel is the best one? We want to, so yeah, because we want to describe the overall performance.
N divided by 2, the average.
Yeah, average n divided by 2. Yeah, how about, do you feel it's a fair way to describe overall performance? Fair way? N divided by 2, he said. Do you feel we can do better than that? N divided by 2, average. Yeah. 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 I want to say close, but not accurate. Yeah, we need to do better. Okay? We need to do better. Yeah, but it's the direction is good. Okay, yeah, some average, but what average? Now we need to do better. What average? Right. Because here, when you take average, you also need to consider the no match case. Okay? No match case. How large is that no match case? Right? You don't know. How large? What's the probability that a given key does not appear in the array? We don't know, right? We don't know. It's not given, right? Yeah. Yeah. So we need an assumption on that. We need an assumption on that. Yeah. All right. So first here, the best case is 1, right? The best case is 1. Yeah. Best case. 1 comparison. Smallest possible number of comparisons. The worst case. Worst case, n. But there are two possible cases. One is a hit case. Hit. Yeah, we find it. So it's a search hit. Okay, we find it. Hit case. Next one, miss case. Miss. Yeah, we cannot find. So it's a miss case. Yeah. All right. Yeah. N comparisons. These two cases. The worst case. Yeah. But next question, what's the average case? Average case. Yeah. The question, how do you define average, right? How do you define average? Yeah. You have these numbers. When you want to apply certain average on these numbers, how do you define the average? Add all the numbers divided by. Yeah. 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 So here you need to be careful. Yeah. All numbers, yeah, because that problem is you don't know the probability of that no match case. What's that probability? Because the average is related to the probability of that no match case. Okay? Yeah. Yeah. All right. How to measure the overall efficiency? Not the best case, not the worst case. So we need to do the average case. But when you do work on the average case, you need to know that the probability for this case. What's the probability? Right? Yeah. 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 So only when you know that probability, then you have a way to find the overall average. Overall average. Yeah. All right. Yeah. So here we need to make some assumption. That probability on that assumption. Yeah. All right. Yeah. So here, the average case efficiency. So let me see. I have about 5 minutes. Let me see if I can complete this this topic at 5 minutes. Yeah. All right. The assumption is, assume that for the first n cases, yeah, they have the same probabilities. That's reasonable, right? So for 1, 2, you know, all those cases, same probabilities, yeah, evenly distributed. Yeah. All right. But for that no match case, yeah, we cannot assume same probability, right? That's not reasonable, right? Yeah. So here, for the index case, we assume p probability. Then -1 case, yeah, because function return -1, so that's the no match case. Yeah, that's the complement part, 1 minus p. Complement part, 1 minus p. So with this p number, then we can define that average. We can find a fair way to define average. Now, you need to know this p number. Okay, all right. After we know this p number, this time when we calculate the average, we need to use the special average. We call it weighted average. Weight, assign suitable weights. So it's the weighted average. Yeah. How to get a p? By experiments. Okay, by statistics. Okay, real world. We collect data in the real world. Do statistics. Yeah, you know, history data. So we get that p. Yeah. All right. Yeah. So you just know there is some way to estimate that p. Okay. All right. Then with that, now we do weighted average. Now, so here we assume 2 subcases. Okay. So the hit case, the first subcase, the miss case, second subcase, 2 subcases. The first subcase, what is the average of the first subcase? Yeah. Average of the second subcase, first subcase, average of the first subcase, then you can do your normal average. Yeah, because we assume they have the same probabilities. Yeah. Then that usual average, yeah, it works. Okay? Yeah. But 1/2 times n plus 1. Yeah. 1/2 times n plus 1. So that's for the first subcase. It's average. What's the average of the second subcase? Second subcase, only 1 case, right? What's the average of that 1 case? The same number. 1 case? Yeah. Yeah. When you take average, that same number. All right, so that's n. Okay, all right. Thus, after that, you need to do weighted average combining these 2 subcases. Weighted average. What's the suitable weight? Probability is the suitable weight, right? The probability. Yeah. Probability for the first subcase, that's p. Probability for second subcase, that's 1 minus p. That's the corresponding 2 weights for these 2 subcases. So when you do the weighted average, this is your weighted average. The first average multiply its corresponding probability, and the average of the second subcase multiply its corresponding probability. That's the weighted average. That's the weighted average. Okay? Yeah. All right. So this formula gives you the weighted average. That's the, formula. That's the accurate formula, precise formula. Okay? All right. So here, one thing you should know, we should use the weighted average to calculate average efficiency number. All right, yeah, that's it. Yeah. So let's stop right here. Yeah. We will do our first quiz this weekend. Okay, I will assign you the first quiz this weekend. The coverage at this point. Okay, this right here, this point. this slide, okay? Coverage from beginning to this place. The canvas, yeah.
Will we proctor or?
No, yeah, not proctor, not proctor. The proctor thing, I will think about it, yeah. Oh, no, for your in-person class, we do not, because you do tests in classroom, so no proctoring, okay? No proctoring. In-person class, no proctoring. Don't worry, don't worry.
Monday. This is in person class.
Online,
Online.
online. 1 week duration, greater or equal to 1 week, okay? Greater, yeah, more than 1 week, a little more than 1 week duration. Yeah. Yeah. Mainly to help you study. You need to familiar with the material. So you have plenty of time to study.